Welcome everybody to our second Power of Knowledge lecture. Sorry, I'm multitasking. I'm letting people in from the waiting room. Yeah, it's awesome to see so many people of you joining us tonight. We started off 3 weeks ago with Alice Schmidt giving us a general overview of how to solve the sustainability puzzle. And today I'm excited to welcome Lindsey Nicholson to our lecture. Lindsey is a glaciologist, and her interest in glaciers started in geomorphology, understanding how the hills of Scotland were shaped by ice, and have brought her now to being an assistant professor at the Uni Innsbruck. She teaches glaciology and climate science there and is involved in outdoor science, education through Girls on Ice Austria and the Juno Icefield Research Program. And on the side, which is really interesting, I think, she's studying a master degree in art and science at the University of Applied Arts in Vienna. And yeah, when she's not doing any science stuff, she prefers to spend her time on a snowboard. And yeah, thank you that you're joining us tonight, Lindsey. And I'm very excited about your lecture.
Thank you, Christina. I'm just going to dive straight in with sharing my screen here. Do let me know if there's any technical problems by speaking up. So I thought I'd start with just this. When we're talking about climate change, we're often thinking about how warm is our planet, basically. So I'll start with the question, what temperature will a planet have? Now, the governing thing about this, oh dear, I can't move forward. So technical problems are on my side. Here we go. And basically the temperature of a planet will rise and fall. Just a second, has the slide advanced to a different one, please?
Yes, it has.
Okay, thanks. So the temperature of a planet will rise and fall in response to the balance of energy coming in from the sun, which heats the planet, and energy emitted, which cools the planet. And it will rise or fall until these energy inputs and outputs are balanced. And this is to conform with the laws of energy conservation, basically. And the energy coming in from the sun can change as a function of the Earth's orbit around the sun, and also various things like the sunspot activity, and also partly how reflective the Earth's surface is to shortwave radiation, so the visible radiation we see from the sun. The emitted energy is emitted actually as a function of temperature. It's the long wave radiation that we all emit also from our bodies. And it changes kind of as a function of how the whole climate system of the Earth, of our planet, changes, to do with what the atmosphere is made of and how the land surface is covered and what's going on in there. Okay, and one of the reasons why it's important to understand this balance in its core is that when climate scientists talk about changes to the climate system, it's often chosen to express it in a term called a radiative forcing. And when you see that, it's about this, like talking about how much does any change in the system, how does it equate to a change in this radiative balance from the shortwave radiation, the solar radiation coming in, and the long wave radiation going out. So it's a kind of unit that we express it in because this balance so fundamentally governs the temperature. So, for example, of our Earth, where it sits relative to the sun, if we had no atmosphere at all, these two radiative forces, the in and the out, would balance with a global mean temperature of -18, which thankfully we don't have. When we add the atmosphere, when the atmosphere developed on Earth, what it means is that for a period of time, the incoming radiation exceeded the outgoing long wave radiation because this was trapped within the atmosphere, what we understand as our greenhouse effect. And as a result, the temperature had to rise until the outgoing radiation at the top of the atmosphere. So the whole system has heated up and been in a higher energy state until the the emitted radiation at the top of the atmosphere equals what's coming in. And the temperature that happens sort of is about plus 14, 15. And that's what we have now, which is pretty cool for us because it helps life exist. So this is the well-known greenhouse effect, and I won't explain this, but this is kind of the what makes life possible on our planet. And because our human activities have such a profound kind of effect on the composition of the atmosphere and changing this, and this is a profound control on our planet's temperature. This is why it's a very powerful kind of control knob that we're turning. Okay, so that the key thing to remember is that this incoming solar radiation at the top of the atmosphere actually has to equal this emitted from the top of the atmosphere based on its temperature. So this climate system that I talked about is made of kind of 5 big components, and these are depicted in these pictures on the right. So there's the atmosphere, the biosphere, the lithosphere, so all the land surface, the cryosphere, so all the frozen water, and the hydrosphere, or the liquid water. And basically, the atmosphere, for example, shunts energy around really fast. The hydrosphere exchanges with it, but also shunts energy around really slowly in the big ocean circulations. The biosphere is important for cycling carbon and atmospheric gases at like quite high frequencies, so quite rapidly turning it over, while the land surface is part of this very long-term carbon cycle by which carbon can be buried with the ocean floor being subducted under where 2 plates meet as on the Earth's surface, and also carbon can be emitted from like volcanic eruptions. So there's a bunch of ways in which this natural, and when I say natural, I'm talking about non-human intervention, although we of course are part of the natural system, we emerged from this system. But so without humans, there are various ways that this can change. The formation of the atmosphere, solar variations in the orbit, eruptions, asteroid impacts that we kind of know about in terms of their relation to mass extinctions. And also, we're not the first sort of life form to change the planet, and particularly through changing the composition of the atmosphere, because I've put down here the evolution of life, because the evolution of life kind of profoundly changed the composition of the atmosphere. Okay, so these natural cycles have caused pretty substantial changes. Here's the Earth like 800 million years ago. It's a time called Snowball Earth, and the planet was almost entirely ice covered, and the only way it kind of got out of this is thought to be through large-scale eruptions that made a kind of hyper greenhouse effect. Then 100 million years ago, we had the time of the dinosaurs, and there was no ice on the planet, for example, and a much warmer global temperature. So we know there's this long history of Earth's climate system evolving, but I think what's more relevant to us and what we're talking about is our impact on the planet and what we've done since the sort of development of our species, and in particular the recent development. And I just put a ton of numbers on this slide. So in 1960, we were 3 billion people on the planet. By 2020, more than doubled to 7.8 billion. We poured about a kilogram, of concrete poured per square meter of the Earth's land surface, which is pretty nuts. The 50% of the land surface has been altered, and I think everybody can understand that who's been in a plane and ever looked out of a plane window. Like, unless you're flying over like boreal forest in northern Russia or northern Canada, you're always seeing modifications by human activities. And most importantly, here we've burned about 40% of the known oil reserves in a period of 60 years. And particularly important because the Earth system works in cycles. These oil reserves and fossil fuel reserves took hundreds of millions of years to form. So we're doing kind of things at a very different timescale to the non-human natural system. Yeah. To put this in graphical form, we can see here at the top, we see in green the carbon dioxide in parts per million, in orange the methane, and here the nitrous oxide. And you can see over time since 1850, just plotted the progressive increase in the greenhouse gas concentrations. And I'm pretty old, so like the carbon dioxide has actually increased by 24% over my lifetime alone. And in the bottom panel, I'm showing the changes in sort of carbon dioxide emissions from all this fossil fuel cement and flaring, like attributed to causes, and also this lesser part in the kind of khaki green about the way that we've changed the emissions by changing the land use. Okay, so we know this because we can measure these with atmospheric concentrations of these gases, and also now we can measure them by satellite determination by assessing the composition of our atmosphere from space, which is also pretty cool. And because of the rapid change after this 1950 period, there's quite a strong movement in Earth science to term this period from 1950 onwards and the Anthropocene. Just because of our profound impact on the planet. And I thought I'd start with saying, like, as a result of all these changes in the atmosphere, as we know, we change our atmosphere, we increase the greenhouse effect, then what means is more energy is coming in than is going out, and this energy is stored within the climate system. And what you're looking at the right is since I think 1971 is where the chart starts, which is why there isn't a number 1970 here. Towards 2010, this is the accumulated energy in the climate system over this time period in zettajoules, which is, I had to look this up actually, it's joules times 10 to the 21. And what I want you to look at here is that extra energy is almost more than 90% is going into the ocean, depicted by these two blue things. So this is warming the ocean, basically. It's really acting as a sponge to warm that up. And if we look at these other things of like particular interest to me is the white band, as a glaciologist, the white band, which is all the energy that's being consumed by melting ice. So this isn't accumulating anywhere because actually it's being really used up in turning the solid water into liquid water. The brown stripe or browny orangey stripe is warming the land surface, and that tiny little one underneath the purple is the part that's the actual atmospheric warming. And compared to these like zettajoules, I just thought I'd write that actually there's thought to be the total global oil reserves are thought to contain about 8 zettajoules of energy. So this makes this look like a massive number, but bear in mind that I think there's 15 zettajoules of energy of sunlight comes in every day. So but this accumulation is mainly going in the ocean, and actually only a small part is warming the atmosphere. So when we look at things like the famous, or I think quite famous, I hope so, global warming strikes developed by Ed Hawkins, this is 1850 to the present day, global temperatures represented as a kind of blue to red, blue being cold, red being warm, and scale. When we look at global air temperatures like this is really like the tip of the iceberg. 90% of this energy that's been taken up in the climate system is in the ocean. So I thought I would talk about how do we do climate science a bit. So there's some kind of terms and terms of reference, and I hope it'll be interesting to just clarify what we do. So the first thing is, if we're trying to look at change, we need to understand what is changing. So here's some examples. The top left is the Northern Hemisphere spring snow cover, then the top right is the global average heat content, then the bottom left is the Arctic sea ice extent, and then the bottom right is the global average sea level change. And just to throw out the question, which of these is changing? And I think we can all agree that this bottom right one is showing a kind of continuous increasing trend, the top left one, tricky to say, and the bottom left one is kind of doing some sort of step change around like 1950, just after. So there's different kinds of change, but obviously as scientists, we have to do a little bit better than eyeballing this kind of stuff like I just did. So I thought I'd explain that the way we formally detect change in any of these climate parameters is explained in this schematic. So basically there's a distribution of value, just say this is temperature. So over a reference period, the global temperature, for example, changes quite a lot from year to year because of all the internal variability. You might have heard of El Nino, you might have heard of even the North Atlantic oscillation, and these just affect how effectively the energy can be distributed around the planet, and it wobbles around quite a bit. So this variability has some extremes and a kind of mean and average value. And so this can be described for a reference period as an envelope of variability. And when the mean pops outside that is when we say, okay, something's changed. So there's really a formal definition of how we say and how we know something's changed. And the variables that are monitored are described as these essential climate variables. And these are defined by the World Meteorological Organization. And you can't really see in this diagram, sorry, this is on their website though, but there are all kinds of physical properties like the ocean temperature, the ocean acidity, greenhouse gas concentrations in the atmosphere, upper atmosphere ozone, lower atmosphere ozone, the productivity of the forests. There's just heaps of things in all these 5 like climate spheres that are measured that we use to kind of more or less take the pulse of the whole climate system. And they're kind of recorded in very standardized ways that are governed by organizations like the World Meteorological Organization. They do a lot of work into making sure that these records are as consistent as possible over time, even when new technologies are introduced. So there's a pretty like formal process of how these are all measured, and then how they're, as I just described, how a change is detected in there. So an example of like detected change, I'm showing you a figure from the latest IPCC report, the 6th assessment report. And what we're looking at is the change in global surface temperature, plotted as a decadal average, reconstructed in the pale blue, and from 1950 onwards, observed from all of these like measurement networks. And we don't really have observations before because we just didn't have the technology to measure temperature in a reliable way, nor were there enough distributed measurements. And this is important to note, this is the global surface temperature relative to this 50-year period, 1850 to 1900. And that's why, like around here, the line crosses this 0 line. And highlighted here also is the warmest multi-century period in more than 100,000 years. So you can pretty much see that this pops outside any envelope of variability, even though there's this kind of progressive decline that happened. There was a cooler period, and now we're popping out of what looked like normal. And this kind of rate of warming is definitely unprecedented in the last 2,000 years. So how can we say what causes this change? So I've put here a recipe for what's called an attribution study, and attribution just meaning like how do we attribute the change to some cause. So first we need these observations. Then we need some kind of history of external forcings, and I would refer back to these figures that I showed, the pictures that I showed before about like the snowball Earth and the really warm dinosaur world, because we know something about how the deep climate of the past has changed based on the geological record. And there's loads of mad fancy research done on paleoclimate, the past climate, from these proxy records, which is pretty interesting, sometimes uncertain, but the way we kind of increase the uncertainty is to get evidence from lots of different lines of evidence. So, and if they all kind of agree, then we feel confident. Then we need some kind of physical model. And when I say that, I mean like a system of equations that represents that can connect these, so it can be a kind of process. So it's basically representing the whole Earth system. And we need some kind of estimate of how much we think our Earth system varies internally. So a kind of noise signal, like the wiggles and the lines we just saw in the previous plots. I can answer questions on what these climate and Earth system models are like later, but I'm just leaving it there for now. And then what we do is you run a simulation of this model with and without certain forcings of interest. So for example, let's just make it really simple. We've got our observations in the black wiggly line. We run a simulation here in the blue, removing the forcing that's caused by human behavior. And so this is why we need to know what was the paleoclimatic forcing before we existed at any sort of significant numbers, because then we can say how we expect this behavior to continue in the future if we weren't involved. And then we can add in the human forcing, and we can see which one matches most closely. And obviously, when I say which one matches most closely, that's actually done with a statistical test rather than let's see which matches. And so here's another figure from the latest IPCC report showing exactly that. So I set you up nicely. And so this is showing how we can attribute that temperature change, and here only showing from 1850, so just the last bit of that previous graph, can be, particularly since 1950, well attributed to all the forcing that we put in. So when we put the human and the natural environment forcings, then the climate models most closely track what we actually observe in our measurements. And if we take away the human part and only do the natural simulation, then this is what would the expected climate evolution over the last 70 years would be more of a flat line. And so this we can use to quite confidently say, yeah, our forcings are what's leading us to our current observed temperature change. The latest IPCC report also does this for looking at not only the trends in the mean global temperature, but also extreme conditions. This is a map of the world, like expressed as hexagons. And these are labeling regions like NEU is Northern Europe. Okay, so then you can probably figure out the rest of it. And what we see here on the left is the whole plot is showing the hot extremes, like temperature extremes. Red showing increases, dominant, decreases, none, low agreement. So that when the different models, some say there's an increase, some say there's a decrease because they're dynamic systems with a certain chaotic component in them. And the dots are showing you how confident we are that there's a human contribution. So the dots are showing the attribution part. So we can see, like, of relevant places to us, this whole Northern Europe and Eurasia is likely to have more hot extremes, or no, rather has experienced hot extremes up to now. These are the observations since the 1950s. And of those, it's pretty confident that all of the hot extremes up here have been attributed to human behavior. So that's where we are just now. We know our environment is changing because we've measured it. We know it's us because we've done the studies. And then next question is, how do these cause changes in other parts of the system? And the important terminology there is feedback, and there are positive and negative feedbacks. And lots of people think that a positive feedback must mean kind of warming, but it's not really, it's just an enhancement. So it's like, if it exacerbates the situation or if it fights against it. So for example, if you do have warming and you create a change which speeds up the warming, this is a positive feedback. And then if you have global warming as your starting point, which causes a change, which actually acts to slow down the warming and puts the brakes on it, that's a negative feedback. So let's look at an example of a feedback. This is the Arctic sea ice, the extent shown here in the visible color plot from the end of the summer in 2020, compared to the yellow line showing the average of 1981 to 2010. So what happens when we remove all this ice is the ice surface here over the ocean reflects quite a lot of the solar radiation because it's bright and white. We all know it, why we need our sunglasses and our sunscreen over the snow. And the ocean, by comparison, reflects only about 7%, so absorbs almost all of the radiation coming in. So what that means is that more energy is being absorbed, which exacerbates the warming, which exacerbates the ice loss. So it's a positive feedback loop. And in fact, the feedbacks associated with the loss of polar sea ice at a global scale over the last decades have been equivalent to even about the radiative forcing of about a quarter of the human greenhouse emissions. So this is a massive feedback that's running out of control. And we expect that quite soon there'll be at least 1 year per decade where there's no sea ice remaining. So I wanted to talk a little bit about types of response. So the top diagram shows a curve, which is some kind of, let's say, a forcing. Right now, we're just talking about, say it's warming. How do these other system components of the climate system respond? Like the sea ice retreating would be an initial response, which is part of a feedback loop. And I want to talk about two things. Firstly, I'll talk about this committed change associated with a delayed response, by which I mean, here the brown forcing line is matched in the response more or less exactly. The system changes as in sync with the forcing. If we look at the blue dotted line, there's an end response, but there's a long delay until it starts responding, and it takes a bit longer to achieve its full response. Like, so here we've stabilized already, and then this line doesn't start to flatten out until the end of the graph. And then I want to talk about tipping points and threshold behavior. So as an example of this committed change, I'm talking about glaciers. This chart is showing time along the bottom axis, what would be expected to happen to all the glaciers in the Alps, all the mountain glaciers in the European Alps over time. This is their, on the right, this is their volume expressed as a fraction of the 2017 volume shown by this black dotted line. And the colors are showing which of the expected sort of atmospheric emissions pathways we follow. So this is dependent on how much greenhouse gases we emit, the blue being if we're really good, and the red being now, how we're behaving now. And I want to draw your attention to this black line because this is what's called the committed change. This is how much of the mountain glaciers in the Alps we would lose even if we stopped doing everything. If we stopped all our emissions right now, if we hold the climate system, the atmospheric composition as it is right now, because the glaciers take decades up to about 100 years for the size of the glaciers here in the Alps to respond, they're still responding to stuff we did like a couple of decades ago. So we're going to lose like maybe 35%, or this is what the models say, we're going to lose about 35% of these glaciers, even if we do nothing. But you can still see there's lots to be won between saving 40% of the 2017 glacier volume in the Alps or saving nearly none, depending on what we do in our emissions. But the idea I wanted you to take away from this is this committed change, that some change is going to happen even if we don't do, even if we stopped everything we were doing, or all human activities affecting the planet. Now, tipping points, if you don't know, are changes in the climate system which are basically irreversible. And that's the important thing about it being a real tipping point. There are some kind of thresholding behaviors where we see like stepped behavior, but they might be reversible, some of them. And the ones that are kind of irreversible are what's identified as tipping points. An example is, for example, if the Greenland ice sheet melts, because there's no way the Greenland ice sheet would form under today's climate. It exists, and it's a remnant of a former colder climate, basically, and it manages to, so far, it's managing to survive because it's so thick. It's like 3 kilometers thick, which means it forms a giant icy mountain range, which means it's snowing on top of it. Whereas if you took it off, the ground surface would be like sea level, parts would be below sea level, it would never snow. Or it wouldn't, the snow that would fall there wouldn't survive the summer, more accurately put, it would probably snow, my bad. But you'd have much more rainfall and the snow wouldn't survive through the summer season. So you couldn't regrow it. That's the point, that's the kind of definition of this tipping point. And when you sort of change big old chunks of our climate system, that's expected to have sort of profound knock-on effects. And importantly for us as humans, you know, like we evolved in a very stable climate period of the Holocene, like the whole like development of human civilization. The climate didn't change too much, so we evolved with our current climate system. And if we change these in huge ways, then we're likely to have unexpected challenges to deal with. I wanted to also talk about uncertainty, and to illustrate that, I'm showing you plots of actually the projected, which I haven't really talked much about projected futures, but I need it to explain uncertainty, so I'm doing it here. So the time axis here is until the end of the century, and what I'm showing on the left axis is the global sea level rise relative to 1986 to 2005, in all cases coming from, for the top, Greenland, in the middle, the Antarctic ice sheet, and in the bottom, all the glaciers of the world. So the red line is showing what we expect, how much meltwater we expect to pour into the ocean basins by the end of the century if we follow the emissions pathway that results in a radiative forcing of 8.5, and that's this RCP 8.5. This is why I said it's expressed in radiative forcing often, or the 2.6 pathway in blue. And all these mean is if we behave more or less without imposing strong legislative restrictions on greenhouse gas emissions, and the 2.6 is if we're really good and very active about that. So to read this from the glacier side, we expect, if we're really good, we expect like only 10 centimeters of global sea level rise at the end of the century, or 20 if we're not so good. A couple of things to point out here. the sea level rise won't be evenly distributed, so that's not 10 and 20 centimeters experience the same in all coastlines for various reasons I can explain later. That will be much higher in the low latitudes, like in the tropical oceans. And what I wanted you to look at here is the shading around the line is like our uncertainty. Now, we've done decades, like more than 100 years of research on mountain glaciers, and we understand how they work pretty well. So we've got relatively narrow error bars here. But when we look at the ice sheets, the error bars are huge. We're really not very sure of what's going to happen. And that's not because we're shit scientists. It's because we don't know if there's going to be some thresholding behavior, if there's certain instabilities here. Sea level can seawater rather can actually like penetrate underneath these ice sheets, which we haven't seen happening yet. But if it does, we have to kind of imagine what's going to happen using our models, but we can't constrain it very well yet because it's an area of active research. And the other thing I wanted to point out here is that this matters quite a bit because the Greenland ice sheet and the Antarctic ice sheet are really only now beginning to contribute to sea level rise. In the past, they were pretty stable. And this is a big issue because Antarctica contains more than 90% of the global land ice. Greenland, a bit less, like about 7%, I think. But all the glaciers on the world, all our mountain glaciers that we love so much are less than 1% of all the ice on land. So even though we understand this bit pretty well, it's less than 1%. And the European Alps are less than 1% of the 1%, which is kind of nuts, I think, when I think about how much time I've spent measuring glaciers right here. Okay, so this is that kind of the uncertainty, and I wanted to talk about what will the future hold. And these are these socioeconomic pathways, they're called, but they're projections into the future of what our emissions will be. And here, all our emissions are converted into a unit of gigatons of carbon dioxide per year emissions. So that's what's up this x-axis. So you can see this like 8.5. This is causing a radiative forcing of 8.5. This one a radiative forcing of 7. This one 4.5. So this is this planetary radiative forcing connected to those first slides I showed you at the beginning. And at the right here, I've shown you the expected global temperature perturbation associated with this radiative forcing. And this socioeconomic pathway, denoted by the SSP, is basically a combination of political and economic, will and choices that's described. So you can see here the ones that we like the look of are probably these blue ones, staying at a warming relative to 1850 to 1900, so a kind of pre-industrial warming of 1.5 degrees or 2 degrees. Yeah, and all of these require, as you can see, quite a steep reduction in the emissions per year to be able to achieve this. And even this like yellow one that doesn't meet it requires quite a substantial reduction of our emissions. So this is what we do. We base our projections on, and we say, okay, these are our future scenarios, and then we can look at what the impacts of those are. For example, here we're looking at what the IPCC projects for like 10-year heat events, heat waves, and 50-year heat waves. So things that are things that were in this period, 1850 to 1900, happened only once in every 10 years. What we're looking at, if we look at these dots, is how frequently that would happen in a warmer world. So if we go right out here to a world that's 4 degrees warmer, we would expect 9 out of 10 of those years to like hit this heat wave that used to be a once in 10-year event in a pre-industrial world. And the same on the right for these rarer 50-year events, which are even more uncomfortable. Yeah, and the bottom part is showing how much hotter these heat waves are, and the dots are showing the frequency of their occurrence. So what we can see is the world, when we have a warmer world, we're going to have these extreme weather conditions that cause us a bit of distress a little bit more often. And the same is true for like droughts and extreme precipitation and extremely dry or wet soil moisture events and so on, all things that impact how we operate. Another thing that's super relevant to understanding our choices is that when we plot here along the x-axis the cumulative carbon dioxide emissions since 1850, and this is again in this brutal unit of gigatons of carbon, which nobody understands it really, but it's a lot of carbon. So compared to the global temperature, what we can see in our historical records, where we know how much we've emitted and we know how much the global temperature has warmed, obviously because we're dealing with a dynamic system with some chaotic elements, we've got this wobble, this wiggle, but broadly, this is a kind of linear relationship. And based on this, we can say that every gigaton of carbon emitted converts almost linearly into our temperature increment. So if we look here at staying within this SSP 1.9, so staying within 1.5 degrees, if we go from the present to there, we're really only talking about a carbon budget of 300 to 500 gigatons total to meet this temperature. We can only emit that much more carbon dioxide into the atmosphere if we want to stay within the temperature bounds of this 1.5 here. So it's 300 gigatons if we want to have an 83% chance to stay within 1.5, and it's 500 gigatons if we want to be a bit more risky and say we're happy with a 50-50 chance to stay within 1.5 degrees warming. And that equates to actually 40 tons, based on the current population, 40 tons, not gigatons anymore, 40 tons per person on Earth, total, which is a bit spicy because at the moment, at a global average, the global average sort of gigatons tons emissions of carbon dioxide is 4. 16 in the US, and much less in less developed parts of the world, but the average is 4. So that would mean we can only carry on as we are for 10 more years, which is where all this information came when the IPCC special report on 1.5 degrees and the difference said we've got a 10-year window. That's because we need to change our lifestyles within this 10-year window, because if we carry on as we are for 10 years, then we've crossed this threshold, whatever happens. Staying with this question of can we stay within this 1.5 degrees that was highlighted as maybe a useful goal at the Paris Climate Conference of 2015. And what we see is, this is again this warming to date that we've looked at before. And this is our kind of trajectory. So if we carried on, we would expect to cross this 1.5 line in 2040. 1.5 degrees warmer than this pre-industrial 50 years. And if we look at trying to impose reductions in emissions, what we see is the temperature anyway kind of bobs above this 1.5 line or this temperature threshold and then sinks below. So if we're looking at the blue lines, we're talking about doing some quite fast carbon dioxide reductions. So you've got a higher chance of limiting it, but you still there's a good chance that in the noise envelope or this variability envelope, we bob over sometimes. So that's just a useful thing to think about, that we're probably, even if we're really good, we're probably going to go over it before we can come back down. And the other interesting things I wanted to highlight about this idea of staying within 1.5, maybe this is a complicated diagram. What we see is these P's indicate pathways, ways that we could achieve this net zero in a reasonable time frame to stay within 1.5. So the colors indicate the net emissions from fossil fuel and industry. This brown is the agriculture, forestry, and other land use, which can be both positive and negative, as you can see here. And this is if we go full on for planting lots of trees, using surfaces that can absorb carbon. If we go into regenerative agriculture, then this can be, it's thought that we can flip that land use stuff from being an emissions to an absorption of carbon dioxide, which is good because we need to absorb some. This BECCS, this yellow, is the bioenergy with carbon capture and storage. So it's using burning bio sources of energy, but capturing and storing all the carbon emitted from it. So if we look at the blue line at the top of the gray thing, we can see the sooner we sort of slash our fossil fuel and industry emissions, so the steeper this blue line descends on the left, the less we have to rely upon these kind of negative emissions, I think they're called. So basically sucking carbon out of the atmosphere with either agriculture or carbon capture and storage, which is good because we don't actually have carbon capture and storage at all to the scale of taking like 10 gigatons per year out of the atmosphere by 10 by 2060. That seems a little bit out of reach, although humans are good innovators, maybe it's possible. So the idea is here to meet the 1.5, the net anthropogenic carbon dioxide emissions to have to be down to about 45% of their 2010 levels by 2030, reaching net zero by around 2050 to be able to do it. So all of these pathways meet this 1.5 degree. It's just the one on the left, pathway 1, doesn't need imaginary, not existing yet technologies. The one on the right needs quite a lot of, actually they're not imaginary, that's not fair. Needs quite a lot of current technology to be scaled up just massively compared to what we're currently able to do. Yeah. I wanted to close with like 3 slides about like societal resistance to taking action on climate, because I mean, you're an activist group. I always love this cartoon, you know, like, what if it's a big hoax and we create a better world for nothing? I really see very few negatives of taking action on this. I mean, there's a strong narrative that doing anything to protect our environment is a step backwards and we're becoming more Stone Age and, oh, our economies. But I think that narrative is just really dated now compared to what we can do. And also if we think about what we might want to achieve as a civilization, I'm not sure if we want maximized GDP, and we know we can't handle eternal growth with within the planetary boundaries. You know, we've just got new realizations, and I think people who keep saying those kind of things are really showing their outdatedness. I also summarized here some of the problems I think we have as scientists, climate scientists, trying to communicate this. Basically, I start with saying we kind of bring a knife to the gunfight, because we try and be like, oh no, but I've shown you this fact and let me show you this information. And the people who want to kind of derail action on climate are not bothered about like talking about reality. They just want to plant enough skepticism and doubt that nobody's got confidence about what to do, what's right. So there can be no like positive defining, we got this kind of attitude. And this is beautifully explained in the book and movie Merchants of Doubt. I recommend seeing it to understand what the fight actually is. And it's also explained by this quote here from Mark Morano, taken from the movie: "Gridlock is the greatest friend of the global warming skeptic. We're just trying to stop stuff. We're just trying to stop good shit happening, basically, rubbish." The other thing is that scientists, including myself, probably tend to assume that what we need is more information, and actually this doesn't seem to work. Like, information doesn't change people's minds when they are fixed on a certain worldview. And there's a lot of good psychological research going on to try and tip that balance. And also, of course, there's the fact that like we're on a really unlevel playing field in terms of where all the money is going. Yeah. So these are our big challenges, but I would like to maybe close with this fact that from 2021, the World Economic Forum, who are supposed to probably, you know, the least likely group that I thought would be like pro-environmental action or pro-climate change action. If you look at what they're highest up in their like impact and likelihood matrix of global risks, failure to act on climate is right up here. So even the perceived enemy knows exactly what the problem is. So I think we've kind of got a problem of a non-debate going on almost. We're maybe all on the same side. So I think that's my last slide. I put some key sort of resources that I think are useful in case anybody wants them, but I think I'm going to stop my slide share. I can always share them in another way after.